For 12, blast radius 72 meters. TNT equivalent 2,300 kilograms. 30 kilometers from North Korea's southern border, over the Injin River, a steel truss bridge spans 80 meters across moving water. Estimated enemy arrival, 1 hour and 43 minutes. South of the river, 300 retreating soldiers. North of it, open terrain. If the bridge stands, the crossing remains possible. If it falls, the advance is delayed. Lieutenant Matthew Carson holds the detonation rod in his hand. Fingers steady. Breathing controlled. Behind him, 5 men waiting. In front of him, not the enemy, but a calculation. Carson is 23 years old. Third in his class at West Point. For semesters of structural mechanics, bridge dynamics, shear forces, load paths, safety factors. On paper, structures behave. On paper, failure can be predicted. But this bridge is not a drawing. It is 60 tons of steel assembled into 5 primary load-bearing trusses, 12 support nodes, riveted joints, diagonal bracing members, and a redundancy ratio no one fully documented. The demolition plan is precise. 14 explosive placements. Charges set beneath the primary lower chords at both ends of the bridge. Additional loads fixed to the base of the central support columns. Each detonation point contains approximately 165 kilograms of TNT equivalent explosive. The model predicts progressive shear failure from bottom to top. Destroy the columns. Remove vertical support. Force the superstructure to buckle inward. Collapse toward the center span. Total structural failure within seconds. The theory is sound, but it rests on an assumption. Carson has calculated the structure as a unified mass. A rigid object. A single system responding simultaneously to force. What he has not fully considered is that this bridge is not a rigid body. It is a network of load-sharing elements. A structure designed not just to stand, but to survive damage. The bridge was built in 1936 by Japanese engineers. Main span 48 meters. 2 side spans, 16 meters each. Designed load capacity 250 tons. In practice, likely higher. The truss geometry distributes force across diagonal and vertical members. Each element carries tension or compression depending on load direction. This geometry creates resilience. Damage one member, and load transfers to others. That transfer is instantaneous. Demolition does not reward resilience. The blasting circuit is wired in series. Theoretically near simultaneous. In practice, microsecond delays between charges. Under normal conditions, insignificant. Under dynamic structural response, critical. A blast wave travels through air at roughly 340 meters per second. Through steel, much faster. Each detonation creates a pressure front. Those fronts interact. Reinforce. Interfere. Dissipate. Carson has calculated static shear limits. He has not modeled dynamic wave interference. When TNT detonates, it generates pressures approaching 20,000 atmospheres at the point of contact. That pressure decays rapidly with distance. Direct contact members receive maximum stress. Internal diagonal members receive only indirect impulse loading. Indirect loading may deform, but not fracture. Carson tightens his grip. He presses the switch. 14 detonations ignite within half a second. Fire erupts beneath the bridge. Stone and metal fragments scatter outward. The shockwave strikes his chest. For several seconds, there is nothing but smoke and vibration. Then the dust begins to clear. The south end has dropped. One primary lower chord has fractured. The central span sags. But the north end remains intact. The structure tilts at 12 degrees. Twisted. Damaged. Not passable by vehicles. But not destroyed. Carson does not move. His mind runs the equation again. 2,300 kilograms of TNT. Roughly 9 billion joules of energy. 60,000 kilograms of steel. The energy required to lift that mass 1 meter is roughly 600,000 joules. The explosion theoretically contained enough energy to launch the entire bridge 1,500 meters upward. And yet it stands. Because energy is not equal to applied force. Blast energy radiates outward in all directions. Into air. Into water. Into rock. Perhaps 10 to 20% coupled directly into structural members. The rest dissipated. Converted to heat, shock, vibration. Carson's first error was treating the structure as statically loaded. Static analysis assumes force applied gradually and maintained. Explosive loading is dynamic. Under dynamic impulse, materials can temporarily withstand stresses higher than their static yield strength. Steel that would fail at 500 megapascals under steady load can survive nearly double that under millisecond impulse if duration is short enough. His second error was ignoring redundancy. Destroying one truss member does not eliminate load capacity. The remaining members redistribute the force. Load transfer occurs along diagonal paths. The bridge was not built at minimum strength. It was built with safety factors. Designed for 250 tons. Likely capable of 400. That margin absorbed the partial failure. His third error was asymmetry. More explosive mass was placed toward the south end due to easier access. That end fractured first. The north end, momentarily unloaded, absorbed transferred stresses. Instead of collapsing inward, the bridge twisted. Deformed. Survived. The radio crackles. Status request. Carson replies, bridge partially destroyed. Vehicles cannot cross. Infantry possible. Enemy estimated arrival remains under 2 hours. No secondary explosives remain. All charges expended. Nearest resupply 40 kilometers away. Air support unavailable. Heavy armor absent. The bridge now hangs suspended between failure and survival. Not usable in its original capacity. Not eliminated as a crossing point. In official reports, the incident will be recorded as a delayed advance. Operationally sufficient. Technically flawed. Post-war analysis will identify the issues: neglect of dynamic loading behavior. Underestimation of structural redundancy. Failure to account for blast wave interference. Over-reliance on static calculation models. Absence of contingency explosives. But the deeper issue is conceptual. Carson believed he was destroying an object. He was attacking a system. Systems do not fail the way objects do. Systems distribute force. Transfer damage. Absorb energy through internal pathways invisible to simplified calculations. To destroy a system, all critical nodes must fail simultaneously. If even one load path survives, collapse may be incomplete. This principle extends beyond bridges. Ships, aircraft, buildings, power grids. Each is not a single structure but an interconnected network of elements. Eliminate one element, and the system adapts. Fail to eliminate enough elements at once, and the system survives. Carson will conduct many demolitions after this operation. Each time he will double the redundancy estimate. Each time he will consider dynamic effects. Each time he will ask the question he did not ask at FallThe. What if the structure is stronger than the model? The bridge remains in that twisted state until later operations complete its destruction. For months it stands as a reminder, partially collapsed, partially intact. Neither victory nor total failure. FallThe, 2,300 kilograms of explosive. 60 tons of steel. The math was correct. The energy sufficient. The placement precise. The assumption was wrong. And in engineering, when the assumption is wrong, the structure decides the outcome.